let us prove that if you are given x tau and y say tau prime, given that they are compact topological spaces, then that implies the product space. That means we give the product topology on x cross y with product topology is also a compact topological space. So, for this we will use the following results, namely this we have in fact used already, continuous image of a compact topological space is compact. So, x compact topological space, y any topological space, f from capital X to capital Y, x with the given topology on x, y with the given topology on y. This is compact, y is just any topological space and the map is continuous. Then this implies the image, that is f of x considered as a subspace of y is compact, is also compact. It is a compact subspace of y. We just will give the, we will see the hint. So, that is we have the domain space, this is compact, the codomain is y. So, that need not be compact, but the range, this is our f of x. So, the range is a subspace of y and we have a continuous map f, a continuous map, then x compact imply fx is compact. So, what is hint? So, consider a collection of open sets in Y. So, say script A collection of open sets in capital Y such that that collections covers the range fx. That means fx is a subset of union of A is in script A. So, we have a collections, this is A, like a collection of A's that covers the range f of x, that is f of x is subset of union A is in script A. Now, take the, we have to use the fact that x is compact. So, naturally you will have to get a cover for x, and because x is compact, then we will get a finite subcover, then go back to the range, then we will get a finite subcover for fx. So, so the natural cover for x is comes from this equation, say 1, just the pre-image of the range is the whole space x. Now x equal to f inverse of f of capital X. So which is equal to, which is a subset of, we have fx. So we are writing this is subset of f inverse of fx is subset of union A is from script A. So but this f inverse of union is same as union f inverse of A is from script A. What is script A is a collection of open sets in Y, and our function f from x to y continuous A is open, A on open set, A open set in range, open set in Y. So that will imply the inverse image f inverse of A, this set is say open in, I am writing in short, f inverse of A an open set open in X. So each f inverse of A for A in script A is open set in X, and X is a subset of this union. Of course each is subset of X, hence it is equal to X. So now X is compact, so that implies, hence X is a, that is now X is a compact space, implies we will have a finite subcover, our index set is script A. So that means this implies there exists a natural number n and A1, A2, An from script A, say that X will be equal to union of this, union of f inverse of the I varies from 1 to n. So now again go back, that is all. Now prove that this implies, using this now f of x, prove that this is a subset of union of f of f inverse of ai will be a subset of ai. So this is, just I will write, this is subset of ai, I varies from 1 to n. So that is all, we have this always f of f inverse of ai, this is subset of ai. So use that. So we will get there exists an n and a1, a2, an, such that fx is a subset of this. So that is, we started with a open cover A and we got a subcover. What is our subcover is this a1, a2, an, subcollection of script A, such that now this union covers fx, hence f of x is compact. This is a very useful result. In fact, we have already used it, continuous image of a compact topological space is compact. So now using this, we will see that if you are given a compact topological space. What is our theorem? In fact, this is a celebrated theorem called Tikhonov's theorem. What we prove at the first stage is for the finite product. In particular, just take two topological spaces x and y or x1 x2. So, notation does not matter. We will start with xy, we have started already, x tau y tau prime are given compact topological spaces. Then this imply the product space x cross y is also a compact topological space. So, we will prove that if we start with a open cover for the Cartesian product x cross y, which consists of collection of open sets, but what is interesting is we do not require to consider the collection of all open set, enough to consider the collection of all basic open set. So, because you give any open set can be written as a union of B from some script beta, where union of say B belongs to a subcollection of script beta, where script beta is a basis for the topological space x tau. If we know a given topology x tau and we know that script beta is a basis for x tau, then any open set can be written as union of members of script f. So, each open set can be replaced by a collection of basic open set. So, we will use this fact, that is x is compact if and only if whenever script A is a collection of basic open sets, then that collection has a finite subcover. That is enough to prove. That is a sufficient condition to prove that a given topological space is compact. So, we will have to prove that, let us say, like our some for example, again we have not yet proved closed interval is compact. So, let us say our x may be like closed interval a comma b, a subset of R. This is, let us say, our x, capital Y, say another interval c comma d. I will assume that c less than d, the usual closed interval. Just for example, we are taking closed interval a comma b, y equal to say c comma d. Let us see how the Cartesian product looks like. Then the here this is a closed and bounded interval in R, and c comma d also closed and bounded interval in R. Then the Cartesian product is, so A set of all. So we will consider what is our x cross y equal to set of all order pair, say small x comma y, such that small x belongs to the domain x, small y belongs to capital Y. And we will see that in this particular case we will get the rectangle. So you consider if we take any element in this rectangle. So let us consider this is our rectangle. So if we take any element, say order pair x comma y. So what is this? X, the x coordinate belongs to closed interval a comma b, and the y coordinate so will belongs to, this is y coordinate belongs to c comma d. So we have in this particular case we will get our Cartesian product as this rectangle. So what we are going to prove is if x is compact. So suppose closed interval a comma b is compact for any a comma b, a less than or equal to b, and closed interval c comma d compact, then the Cartesian product is this rectangle, the closed rectangle including points here. Here any point will be of the type c comma x. So this rectangle, which is also, we see that it is a closed set and it is bounded, mean in the sense that it is contained in a ball center at some point and some radius, then this ball, this set, in this case rectangle, will be a subset of some ball. So which is closed, bounded in the metric sense. So right now this is only to motivate how the products looks like. So now for us, just consider the domain space capital X, domain space capital X, you fix an x in capital X. So let us fix. So now, so what we are going to prove is, let us start the proof. How we are going to prove is, start with a collection of basic open set in x cross y, then fix a point x in x, then consider this vertical line. This corresponds to, let us say each element here is, the x coordinate is fixed and y varies from capital Y. That is, we will consider x cross capital Y. This is a continuous image of y. So that is, what is y? You take an element small y in capital Y, the function say gy equal to order pair xy. This belongs to x cross y, this g is continuous, y compact, g of y equal to x cross y. This is a compact subset of capital X cross y. So again, right now we will take this result. I mean it is trivial to say see that this function is continuous, image of this function is nothing but x cross y, hence this is compact. So, to prove, what we are trying to prove is to prove capital X cross y is compact, so with product topology. So, consider, so let, shall we call it script A be a collection of what is important is basic open sets, collection of basic open sets in our x cross y, in the product space x cross y, such that this is a cover for x cross y, such that x cross y, the whole space, hence it will be union of, because we are talking of our cover is a contains basic open set. So, it is of the type say U cross V, where U cross V a basic open set, say let us say U cross V belongs to say script A. So, let script A be a collection of basic open set. So, if we take a from script A will imply A is a basic open set, and we know that what is our basis for the product topology, set of all U cross V, say that U belongs to tau, U belongs to tau and V belongs to tau prime. We know that this collection is a basis for a topology on X, that topology is what our product topology. So, beta is a basis, for x cross y, meaning is for the product topology x cross y. So, x cross y equal to union of U cross V, say that U cross V belongs to script A. Same thing as writing union of A from script A, each A is of the type of the form U cross V. So, now we have fixed X and consider the Cartesian product singleton x cross y. So, now for each small x in capital X, x cross y, just now we have seen that this is y compact imply x cross y is compact. This is a continuous image of the compact set y under the function x comma y, y goes to order pair x comma y. So, this is compact. So, and what is x cross y? Now, x cross for each x cross y is a compact, subset or subspace, is a compact subset of x cross y, the product space x cross y, and x cross y is a subset of capital X cross y, because small x is in capital X. So, and which is equal to union of U cross V belongs to script A. So, hence the same script A is also an open cover for x cross y. So, hence x cross y is a compact space. Now, is a compact subset of x cross y, and this collection script A is a cover for x cross y, imply we will have a finite subcover. That meaning is, this imply there exists a natural number, n belongs to n, and u1 select a1, this say some a1, and u2 cross v2, so this is some a2, like that n members from script A, this is our an. So, now we will remove this notation. So, there exists n and n members from script A such that x cross y is a subset of u1 cross v1 union u2 cross v2 union un cross vn. So, we have this finite subcover for x cross y. Now, see that x is in each member of x will belongs to u1, this is capital, u2 up to un. We have that x cross wx is a subset of u1 cross v1 union u2 cross v2 union un cross vn x cross so we have this x cross y is a covered by this collection of open sets. So, where now this for a fixed x in capital X, this y, we have for this x cross y, we have a cover, we have an open cover ui cross vi I1 to n for x cross y. So, let us assume that x cross y intersection ui cross vi is non-empty for each I. So, that means if suppose for some I x cross y intersection ui cross vi is empty, then delete that particular ui cross vi, the remaining uj cross vj will cover x cross y. So, that is without loss of generality, let us assume that x cross y intersection ui cross vi is non-empty for each I. For each I varies from 1 to n. Then this is non-empty, so hence any element in this set is of the type x comma some y, because this order pair x y should belongs to x cross y. So, the first component is x. So, if we second component is y belongs to capital Y. So, our if this x y belongs to x cross y intersection ui cross vi implies x belongs to ui, and this is true for each I, hence x belongs to ui for all I, and that implies x belongs to intersection ui I varies from 1 to n. So, this we call it w suffix x. This is a open set containing x. So, for each x, for each x in capital X, for each small x in capital X, there exists an open set, say w suffix x in X, such that w suffix x cross y, we will see that this is also a subset of u1 cross v1 union u2 cross v2 up to un cross vn. Once we prove that this wx cross y, that is this is wx, an open set containing x cross y. So, we will get a tube, and this is covered by finitely many members of script A. So, that means each tube will be covered by finitely many members of script A. So, take an arbitrary element in x w here this. Now, let us take. So, to prove this, let order pair a comma say y belongs to wx cross y. Then a belongs to wx, but wx is intersection of ui I1 to n. So, hence a belongs to wx subset of ui for each I. So, a will be in ui. Now, this a is in each ui, this is for all I. Now, we have our y. So, now a is in wx, y is in capital Y. Now, small y belongs to capital Y, and then we have that for y in Y, x cross capital, this x cross y is covered by x cross y is u1 cross v1 union un cross vn. Now, this order pair x and this particular y belongs to x cross y, and this will imply x cross y is in the right side. That imply there exists some j belongs to 1 to n such that order pair x y will belongs to that uj cross vj. So, that means this order pair xy, that means now this order pair is such that y belongs to vj for some j, and hence this implies order pair A comma y. Already A belongs to each ui. So, in particular A will be in uj. This is for all I, take I equal to j. Now, y will be in some vj. So, then this will be in v suffix j. So, hence we have that if we start with an order pair a comma y in W x cross y, then that order pair a y is in uj cross vj for some j belongs to 1 to n. So, hence this will imply W x cross y is a subset of union ui cross vi, I varies from 1 to n. That is, this tube is covered by finitely many members, that members are ui cross vi of our script A. So, this let us call 1. Now, consider for each x in capital X, we have this open set containing x. Now, this set of all W suffix x, say that x varies over capital X, is on open cover, for the compact, for the given compact topological space capital X. So, this is an open cover for the compact topological space X, hence that will have a finite subcover. So, this implies, hence X is a compact topological space, implies there exists say k belongs to n and x1, x2, xk belongs to capital X, such that x is covered by, that means x equal to union of W xi I varies from 1 to k. Okay. So, now for this, now we have W x1 cross y, which is covered by finitely many members of script A, then union W x2 cross y union W xk cross y. So, we will prove that this will cover x, that is x cross y. In fact, here it is, each is a subset of x cross y. So, hence we will have x cross y equal to union of these sets, and each W x1 cross y is covered by finitely many members of script A. So, this similarly each we have a finite unions. So, take order pair x y belongs to x cross y. So, x is in, then x is in capital X, and for capital X equal to union of W suffix xi. This will imply x belongs to W suffix say xi for some I. For some I varies from 1 to k here. So, then that y is already in capital Y. This will imply any order pair x y. So, that will be in, then order pair x y belongs to W suffix xi cross y. See, this is a subset of some finitely many members of script A. This ui cross vi, they are all from script A. So, what in short what we can say is, this is a subset of union of A belongs to say script f suffix x, where script f suffix x is a finite subset of script A. So, then W x this, then our order pair x y will belongs to, then this order pair x y will belongs to A for some A belongs to script f suffix xi, where correct, where script f suffix x is a finite subcollection of the started open cover script A. So, hence if we take any order pair x y, then that x y belongs to A for some script f in x suffix I, and this will imply our started x y. I mean, you start with any order pair x cross y, then x y will be in that particular x cross y, then that will be a subset of some A for some A in script f suffix xi. So, that will imply x cross y is a subset of union of A belongs to script f x1 union script f suffix x k, correct. So, on this each script f suffix x1 is a finite set, hence this is a finite subcollection of script A, and that is a cover for x cross y. So, hence we started with a script A open cover for our x cross y implies there exists a, this implies there exists a finite subcover, that finite subcover is script f suffix x1 union script suffix xk. There exists a finite subcover of script A. A is an open cover for x cross y imply this has a, this imply script A has a finite subcover for capital finite subcover for x, this sorry x cross y, finite subcover for x cross y. So, this implies, that implies x cross y is compact, mean hence finite product of, I mean here x compact y compact mean x cross y is compact. Now, one can use induction to prove that if xi tau I1 to n is a finite collection of compact topological spaces, then the product space phi xi I1 to n is compact, that is each xi is compact imply this product with product topology is also a compact space. Yeah, now quickly let us see that what are the nice compact sets in R. See, intuitively one can feel that, I mean what are the compact sets in R. So, you take any closed interval a comma b belongs to R, A is less than B. Now, we start with a open cover R with usual topology. We have closed interval a comma b subset of R, and that imply closed interval a comma b is compact. So, how to prove? We start with a open cover. So, we can start the collection of open sets in R. So, let script A be a collection of open sets in R such that closed interval a comma b is a subset of union A is in script A. So, this is a cover for closed interval a comma b. See, now what we feel intuitively, we have A, then A will belongs to this union, that means A will belongs to at least one A. So, let us say A belongs to fix some A, A belongs to A for some A in script A, and this A is an open set containing A. So, then there is a open interval containing A, say A to A plus epsilon. So, this right side we are interested, so left side does not matter. So, this will cover, I mean this will be this, we can find an epsilon, so that A minus epsilon A plus epsilon is contained in A. So, in particular take say a Y, then this closed A is contained in that fixed A. So, we have this closed interval A to Y is covered by one member of script A. Now, what is our aim is, this will continue in the next session. Just we will indicate, if we consider a set C such that set of all Y in closed A Y block not equal to A and closed A Y is covered by a finitely many members of script A. So, then this is non-empty and it is enough to prove that, what is aim is, just prove that aim is to prove that B belongs to capital C. That means A comma Y is here, B is here, then closed A B is covered by a finitely many members of script A, and we are through. So, this we will see in the next session. Thank you.